Present relatively new method of matrix spectral factorization, which produce numerical algorithm of such factorization. And spectral factorization, as we know, is the special case of Wiener-Hopf factorization, when matrix which has to be factorized is positive definite. In the classical sense, almost everywhere for each t, this matrix is positive definite. It means self-adjoint and with positive or non-negative eigenvalues. And factorization, in this case, these factors are related with each other. That this is Hermitian conjugate of this factor, which is analytic inside, and this is analytic outside of inside unit circle and outside of unit circle. We consider on the unit circle the factorization, and this is necessary and sufficient condition for factorization. And spectral factor is unique if we require that to be outer. These definitions will follow. And we will provide a method for approximate factorization of for given S, how to find this S plus approximately. The method will be provided and explained. Wiener himself proved the existence of spectral factorization in this positive definite case. So he paid attention that in probability theory, in the prediction of stationary stochastic processes, it played important roles, such a special case. And he tried to develop algorithm first, and since then, because of existing applications, many engineers and mathematicians tried to develop such algorithms, such methods. And these are survey papers on this topic, and this is very recent paper. And the methods in general can be described, many methods, there are few of them are mentioned here. Our method is based on principles, on basic principles of Hardy spaces, and we don't go beyond Hardy spaces. And this theory yesterday was very nicely explained by Evgeny Shargotsky, and I will not repeat it again anymore here. I will just concentrate my attention that naturally we identify functions from Hardy spaces with their boundary values. For p is, when p is more than 1, then this is natural, another characterization of these Hardy space functions. And the definition of outer functions was given also yesterday. This is functions which can be reconstructed from absolute values of their boundary values. And notation will be this. This O means outer. And in matrix case, it means that determinant is scalar function and is outer function in this case. And most difficult theorem we use in this area is Smirnov's theorem, that if function is from HP, and then we know in addition that boundary values belongs to more narrow class of HQ, LQ, Q is more than P, then we can conclude that F belongs to this class exactly, not only to this class. This is a brief notation that function belongs to both class. Actually, we once again identify function with their boundary values. And the generalization, Smirnov's generalization theorem also plays a role, that if we know that function is represented in this form and denominator is outer function, it is necessary. And we know that boundary values belongs to LQ, then in fact it belongs to HQ. We will use nothing beyond these theorems actually during our presentation. And I will start now describing the method, and first of all I will emphasize that this method does not introduce any novelty in the scalar factorization. It uses scalar factorization. It is formula for scalar factorization, and in general it is assumed that scalar factorization is relatively more easier than matrix factorization. Therefore, we reduce matrix factorization to scalar factorization. And we will reformulate this existence of scalar factorization, which is given by this formula, in a little bit different form, which we use in the sequel. That if we have function, say from L2, and we know that its logarithm is integrable, then we can find function with absolute value 0, with absolute value 1. Also here should be sign of absolute value, such that this product is from outer function from H2. This is just another characterization of this theorem. We can just represent this u function in this form, taking scalar spectral factor of this square function and divided by f. We will use this scalar factorization theorem in this form. Now let me start explaining the method. That first we do triangular factorization. This is first step in this algorithm, and with diagonal terms outer scalar spectral factors, outer functions, and off diagonal terms they are just of course not analytic in this representation. So this is first step, and we can by this step we already factorize determinant, because determinant of this factor is product of these diagonal terms and is outer function already. So by this way determinant is already factorized, and we present two easy ways how to point of views how such factorization is possible. First, we can just observe that the same formulas as for numerical Chomsky factorization can be used exactly in the same form as it exists for Chomsky factorization of numerical matrix. Just instead of taking square root, we should make scalar spectral factorization. Otherwise, these formulas are correct and can be used to produce the factorization which was shown on the previous slide. And another point of view which can be used also, that we can just for each t on the unit circle, for each t we can perform numerical Chomsky factorization, and let's denote this factor by this. And here we have positive entries now, and we can just identify classes that these all functions belong to L2, because we have this scalar product of squares of sums of this gives entries of this matrix, so they are integrable, and therefore these entries all are square integrable from L2, and logarithm of determinant we know this integrable, and therefore all these logarithms will be integrable, and therefore we can find functions with absolute value 1 and make them analytic on the diagonal. And if you multiply by this matrix which has diagonal entries this, and we will get that triangular factorization which we had in this form. Okay, this is just first theoretical step which we do, and in practical numerical algorithm we should perform this somehow. We should use these Chomsky formulas, and we should use scalar spectral factorization to perform this triangular factorization. Okay, next, also theoretical developments follows that what we are doing, that we multiply middle term here after triangular factorization, which was already presented. We multiply on the unitary matrix inside, and this formula remains valid in this case, since this is one unity matrix, in such a way that this factor becomes analytic. All entries become analytic with requirement that this determinant should be 1. This condition helps that determinant of this product remains same as determinant of this, and it means that it will be outer. Determinant of this will be outer, because determinant of this function was outer, and this is 1. And also this equation remains valid, so this makes us to conclude that this will be then spectral factor of this matrix. So this equation will hold. So let me explain now in details how, because I think this is important, how do we construct now these unitary matrices. we can multiply by this unitary matrix as much as we like. So several times this equation does not change. So let me denote these analytic entries by plus and non-analytic entries by minus. So we have this triangular factorization, and first we make, for a while I will switch off this. Sorry. So here we multiply by 2 by 2 unitary matrix, which is once on the diagonal, and this makes these entries analytic here. Then I will multiply 3 by 3 matrix, unitary matrix, and then here once, and remaining terms are 0 here. And this product now makes 3 by 3 principal minor here analytic, and therefore spectral factor of S matrix here, principal minor of M 3 by 3 matrix, and so on. In the end, so all these matrices will be automatically unitary, but this corner will be unitary also. And then I will multiply R by R matrix, and this product eventually will be spectral factor of matrix S. Okay, this is represented here. So this product will be, as I told, spectral matrix of S, and for this reason, yes, this each matrix now are described here. So this has this form, as I told, each matrix, and also each of them, this corner has this presented form here, that all entries here are analytic. So these rows are analytic, and last row is anti-analytic functions, and they have determinant all equal to 1. And these matrices are also related with wavelets. But this is topic of another lecture, so I don't concentrate here on this topic. But these are very closely related with. And yes, I missed this. Oh, yes, I missed this picture. That's why I was. Yes, this is a representation which I described here. That this spectral factor will be M this matrix, and U2 is this, U3 is this, and so on. And this is M by M minor, principal minor of this matrix. So after, if we multiply, if we take M products here, this will be spectral factor of original matrix. Principal minor of this matrix, M by M matrix. Okay, and in this, to perform this, the important role plays the following lemma, which we will so describe here now, that moving from M minus 1 step to M, what we have, that here we have, let me draw it separately. Okay, I will. That we have here, this matrix is already m-1 matrix, and this is already analytic matrix, and these rows here are, this row is non-analytic terms, and here we have outer function, and here zeros, and here also non-analytic terms follows, and here these outer functions. And we now concentrate attention to by m principal minor here and try to make analytic next row. This is described on this slide, that we take m by m principal minor here, and this is analytic already, this is already done analytic, and this row is non-analytic, and we are actually taking out this term here and represent this as a factor of these two matrices, and then we make this analytic. And this is one of the main lemma, main theorem of our result, that for every such matrix function where this is outer analytic function and these are just L2 functions, there exists unitary matrix function of this form. Here we have all entries analytic and these anti-analytic functions, they are from H infinity, and determinant is 1, determinant is equal to 1, and the product is analytic already. So let me repeat once again, because this is a main lemma actually of the main lemma and main theorem of this method, that when we have such matrix from this class, we will find unitary matrix with requirement that determinant is 1 and has this special structure that they are analytic and last row is anti-analytic, and the product is analytic matrix function. And we do this numerically. We construct, for given these functions, we construct this matrix numerically. And how do we do? Yes, this is equivalent for. How do we do that? We approximate these non-analytic terms by their Fourier coefficients. We fix some large positive number n, and we make this approximation, and some additional notations that we denote this set of polynomials of degree n by this, and this class, when we stop here, starting coefficients from minus n, we will denote by this, these two additional notations. And we will repeat the same theorem, but now classes are different. These functions are taken from this class. They have Fourier coefficients with negative index, just finite number of them. And we prove that in this situation, there exists the same unitary matrix function with same characteristic, but they are all polynomials of degree n now. So if you have just n finite coefficient, n negative coefficients in this representation, then unitary matrix function for which we construct has also the n coefficients. They are polynomials actually. And this we are doing in explicit forms. I mean that these coefficients, that finite coefficients, negative coefficients, positive coefficient doesn't pay. I mean coefficients with positive indexes doesn't play a role here, and these negative coefficients only are important, and when they are given, and these coefficients also of this function also, we find these polynomial coefficients of this unitary matrix function explicitly. So our reason is that this product should be analytic and determinant should be 1, and of course this matrix should be unitary. And as you see, this is highly non-linear problem. We have these functions given, and we should find, so this function in which has too many requirements, that unitarity is highly non-linear problem, and determinant 1 is also even more highly non-linear problem. But we reduce the problem to linear problem, and we are doing this by introducing this system of equation, which very important, and I will try to rewrite it here because so this up to m minus 1, we do the same, and in the end we have equation actually which would say that this product is analytic. One of term we will write down here. So C1 x1 Cm minus 1 xm plus denotes that we are searching for analytic solutions. We can consider this as a boundary value problem, specific system of boundary value problems. These zeta and f functions are known, and we are searching. They don't play role in our construction, but we need x explicitly to construct the unitary matrix which we are searching for. Now it can be shown that this condition is equivalent to this system, and it is done in some papers. That what is important now that we will just start from this system of boundary value problem, and we will construct explicit solution of this system, and we will show that the solution will be unitary. And in the case when we make approximation and do this, the most important role plays this following lemma, that if we have two maybe identical solutions of this system, u plus and v plus, then their scalar product is independent of t, is constant and does not depend on t. This important lemma has simple proof, and therefore I will present it here, that if we just put v in first m minus 1 equation, and in last equation we put u, and we multiply first equation by u1, the second by u2, and last one by vm, we will get this system from the previous system. And here if we subtract from this equation these remaining equations, we will get this equality here, and it shows that this function is a ratio of these two functions, and here this is outer, and here we use Smirnov's theorem, and we conclude that this will become H infinity function. U and V play symmetric role in this consideration, therefore we can show also that converse scalar product is also belongs to H infinity, so it means that this function belongs to both, and therefore it should be constant. Very simple proof, but very useful theorem, which we use in the sense that we are able, whenever we take just finite coefficients in these terms, finite negative coefficients in these terms, these conditions become linear condition in terms of coefficients of this unknown x, and we will find m independent solutions of this by equating to 0 to the negative coefficients, and having freedom of choosing zero coefficient, non-zero coefficient somewhere here, non-zero number, say 1, we will get m independent solutions. So once again, so we have, for these functions, we have negative coefficients, finite number of negative coefficients, and these coefficients of this function f is also given, and we are searching these unknown functions in terms of these polynomials, and we will rewrite that this condition that negative coefficients, Fourier coefficients with negative index are equal to 0, and for 0 Fourier coefficient we have freedom of select somewhere non-zero term here, and the condition will be translated into linear condition. And in block matrix form, this condition looks like this system. Here, under this notation that these matrices are given in this form, and X is this column matrix, this system of equation looks like this. Here, this D and gamma are coefficients, Fourier coefficients of these functions, and negative coefficients of these functions. As I told, they are only important. And the remaining conditions that when we take this as a columns, these solutions as a columns of unknown matrix U, which we are searching for, and the remaining conditions that it should be unitary and determinant should be 1 is satisfied automatically when we satisfy this equation because of lemma which we have proved. So when we take these solutions of this system, and put these solutions as a columns here, since we knew that this scalar product was constant, we see that this condition will be satisfied. And because of this condition, this will be also satisfied, that this product will be analytic. Therefore, we achieved our goal. We need also to show that determinant of this does not guarantee that determinant is constant with absolute value, but we need determinant to be constant without absolute value. So this can be also proved using again generalized Smirnov theorem, because this holds, and we can see that therefore determinant is function from H infinity. And therefore then simple calculations show that this is inverse of matrix F, and therefore this equation holds. And again we claim that determinant of this, which is this, belongs, since they are bounded functions, belongs to L infinity, and we know that it has this form. This is outer function, and its power is also outer function, and again it belongs to H infinity by generalized Smirnov theorem, and it means that then this is constant. And after normalization, we can take in 1 this matrix V and divide by this, and because of this constant that we have, the product was constant, we can achieve that this product now will be 1, and therefore determinant will be 1, because in 1 this determinant has 1, and everywhere determinant is constant, and it will be 1. So finally we achieved our goal, that for such matrix, let me repeat what we have done. We constructed this matrix which is unitary, and this product is analytic. This was our goal, and actually this finishes the one step of approximating spectral factor. Now we need to prove convergence of the method. So let me repeat once again what we have done, that we had this original matrix with entries from this class, and we cut negative coefficients here. We approach these functions by these functions. Let's now introduce n in our notations. It means that just n coefficients are kept here. And we for such Fn, we constructed unitary matrix Un such that this was analytic, and now we want to show that this is convergent in L2. This describes convergence of our method, of the algorithm. So first of all, observe that this matrix is spectral factor of this matrix, because this is unitary matrix, and this product produce this product, and determinant is also outer function. Therefore Un is defined up to constant right unitary factor because of uniqueness of spectral factorization. And without loss of generality, we can assume that this is positive definite at the origin. For example, this is already H2 function, and entries are H2, and we can define it in the origin. And of course we need some to keep in this representation, to keep same uniqueness property in order to achieve convergence, and we assume that they have same uniqueness property, that all they are positive definite in the origin. And now we prove the convergence using two properties. That first we show that every convergent subsequence of this converge to the spectral factor of this matrix, of this factor, and to specific spectral factor which is positive definite at 0. And next we prove that we show these two properties, that every subsequence of Fn contains a convergent subsequence. And from classical theory of limits, it means that the limit exists, and this is since we know that this spectral factor is unique, it means that from these properties follows the convergence of not only a subsequence of this, but also of this sequence itself. Let us do this step by step. So we will first property is easier to demonstrate, because if we assume that this is it has subsequent convergence, and let us denote by the same n. If we assume that this converges to psi functions, for example, then this limiting function we have the same all properties, that it will be yes, it will have this property also, and it will be analytic, limit will be analytic, and the determinant will be same, because determinants of this does not depend on n, and it will be same. And at the origin it will be first non-negative, but since we know that determinant is positive, we can conclude that it is positive also. And because of this convergence, we have that this converges in L1 also, and it means that they are same as this, and this means that this converges to same. Since we have this convergence, it means that we have this convergence, and it means that this and this are same. So by this way we prove that if we have some convergent subsequence, then it converges to spectral factor of this function. This has all characteristics of spectral factor, which is unique. And next, a little bit more difficult, but I tried to explain this without intensive formulas, that we use the compactness of these operators, Hankel type operators, which acts from this space to this space, to these operators we consider. And from this we conclude that first of all we introduce these projections, positive and negative projections, p plus and p minus, and if we consider, this shows that p minus of this function is 0, and we can take from any convergent subsequence, we can take that negative parts of these functions will be convergent. We can, because of convergence of this, if we take any bounded sequence here, this will be convergent, and from this convergence we can negative parts make convergent, and since this is 0, we can conclude that the negative part of this is convergent, and positive convergence of positive part we can conclude from this, and we will get that this is convergent, and therefore then we can step by step prove the convergence of these terms also in the similar way. And we will, by this way, we will prove convergence of positive part and negative part of this function separately, and we can then divide by f plus, which does not have 0, and we can prove that this converges at least by measure, and then we can prove that therefore this is converges in L2 norm as well. And then after having convergence of these terms, we will consider also these terms and prove the convergence of these terms in analog way. So now actually I forgot one place in the my presentation. Let me return to linear equation which I described. Yes, I forgot that this linear equation eventually, that it has solution can be done also. I did not present it these formulas here, that we can express this x1, x2 and in this form from this equation, substitute here, and we can reduce to 1 n by n equations, this last row, and we can prove that the corresponding coefficient matrix is positive definite and determinant is remoted from 0, and actually it has solution, and we can prove that this solution exists. And furthermore, the matrix which appears here as a coefficient matrix has displacement structure, and this matrix for some applications and for some approximations n might be quite large, but we are solving n by n matrix, n by n linear equation to solve this system. But it has also displacement structure. Displacement structure is special numerical analysis technique, and I will not explain now details here, but instead of n-cube operations, which are standard for solution of linear equations of order n of degree n, we can reduce to solve mn square operations to solve this equation, which is necessary to obtain a solution of this linear system of equations. In some applications, it is mentioned in some other papers as well that this reduction is important. Okay, actually by this I have finished description of this method, because I have shown that the process is reduced, actually nonlinear process is reduced to the system of linear equations, and these equations can be solved effectively. Of course, in practical computer program, you need not most of these proofs. What you need just a solution of these linear equations, which is important, and scalar spectral factorization and triangular factorization. This is two steps actually which are presented in computer code of this algorithm. Yes, the proofs presented in this, which I presented now, are in these two papers, and most probably they are free from errors, but what from application point of view most important are that the algorithm itself is how sustainable is against measurement errors which usually exist in practical applications. And if we want to apply this algorithm in practice, we should check and we should have some guarantee that this algorithm works for such situations where measurement errors usually exist for data when we construct power spectral matrix, which has to be factorized. And of course this is very subtle topic, because we do know that factorization even in scalar case is not stable in general, and if matrix is singular, if it has 0, even in the scalar case, if function has 0, then small change of this function can be can cause a big change of this function. In general, this was described yesterday on Evgeny Chargotsky's talk also, this problem. And in some case anyway, since we are reducing the problem to the scalar case, if matrix which we construct is deterministic and singular matrix, for example, which are useful in some wavelet constructions, and we have been able to factorize such matricing by reducing to the scalar case, because in scalar case, if you have deterministic 0 on the unit circle, then you can factor out this 0, actually maybe manually even in some cases, and you get what you get. You can obtain nice matrix which can then factorize numerically by application of your algorithm. So by this way we have factorized several singular matrices which is applied for wavelet construction, and this is presented in this paper. But furthermore, we have hope that our method is sustainable for measurement errors. And what makes us to think about in such a way that when we have singular matrix, actually this singularity is transformed into this, when we make triangular factorization, the singularity is translated into the singularity of this function. And the proof I presented, I used that this function was outer function. But in practical numerical computations, because of round of errors, when you make triangular factorization, this, if it is singular and after practical computation, this matrix might not be any more outer function, and it might develop some zeros inside of unit circle. But anyway, the theorem which we presented is correct in this case also. We can just require that it is not 0 at the origin. Otherwise, it's not necessary to be outer function. The construction process which we described works in this situation as well, and the convergence also can be proved in this situation. And this theorem is presented in this paper, spectral factorization with perturbed data. And we have some further arguments to consider that this theorem is sustainable with respect to measurement errors, because this is application of our algorithm in neuroscience, very recent paper which appears. And there is some computations in this paper produced, relied entirely on our algorithm as it is described in this paper. I have some citations from this paper, and the algorithm is characterized as accurate, robust, and we hope that it played important role in these computations. I will conclude. So for real-time applications of the algorithm, it's also important how when factorization is required to be performed almost instantaneously, it is also important how data arrives on equipment which performs these measurements and constructs in real time power spectral density matrix, which has to be factorized. As much as we are aware of results of applications of the algorithm in aircraft control systems by means of wireless communications, this was the project at Maryland University which became interested in Janashia-Lagvilava method at the early stage of the project development, and they applied this algorithm, and we have reports that this was successful applications. Professor in communications at Maryland University, Lasha Ephremidze, is responsible for these applications, and this similarity of these names is just coincidence. Okay, I will finish by this, and thank you for your attention.
Thank you. Suggestions?
I have just one small remark. I was impressed by this patent which you produced, right? And especially by the fact that the first family name is like yours.
Yes.
What does it mean? I mean,
Nothing else, just coincidence, as I told.
But I mean, certainly it's a common root, so maybe you should dig more deep.
The father,
Probably, yeah.
father of this Ephremidze was born in Georgia, in Batumi, but nothing else.
But it's very strong. It's very strong.
No, I mean this was not related.
The owners of this patent have roots in Georgia. That's fine.
Okay, if there are no other questions, yeah.
So in practice, how easy is this method to use? So the recent paper in PhysRev-E, did this take months for them to apply, or was it fairly simple? Do you think?
If you write code, maybe you will need more than a month, but whenever code is ready, then you can apply easily. And I have ready code, and if someone is interested, we can exchange and communicate.
Okay then. Let's thank both speakers again.
Thank you very much.